Hello everyone. Imagine this simple situation. You are holding a coil of wire and you push a bar magnet toward it. Suddenly, a current appears in the coil. Now the big question is, in which direction does this current flow? In the year 1834, Heinrich Lenz answered this mystery. He discovered that nature has a rule. The induced current always flows in a direction that opposes the very change that caused it. This became famous as Lenz's law. If induced current helped the change instead of opposing it, energy would come out of nowhere, violating the principle of conservation of energy. So Lenz's law ensures that electromagnetic induction never breaks energy conservation. Now let us look at the mathematics. Faraday's law of induction gives the induced electromotive force. It is written as E equals minus dphi divided by dt. Here, E is the induced electromotive force measured in volts. Phi is the magnetic flux measured in Webers. dt is the change in time measured in seconds. The minus sign in this formula is the direct representation of Lenz's law. It tells us that the induced electromotive force always resists the change in flux. Think of it this way. Without the minus sign, the equation would mean that induced current helps every change. That would allow free energy, which is impossible. The minus sign makes sure that energy conservation always holds true. Now let us connect this to an experiment. Suppose the north pole of a bar magnet moves toward a coil. In this case, the magnetic flux through the coil increases. How does the coil react? The coil produces a current such that the face of the coil behaves like a north pole. This north pole repels the approaching magnet. Now imagine you pull the magnet away. In this case, the magnetic flux decreases. The coil responds by producing a south pole at the same face. This south pole attracts the magnet, trying to keep it close. So whether the magnet moves inward or outward, the coil always resists the change. This is the perfect demonstration of Lenz's law. Next, let us consider loops of different shapes moving out of a uniform magnetic field region. When the triangular loop moves out, the magnetic flux linked with it decreases. By Lenz's law, an induced current flows to oppose the decrease. The same happens with a square loop or a circular loop. As each loop leaves the field, its flux decreases and current appears in a direction that maintains the flux. The shape of the loop only changes the path of the current. But the principle stays the same. The induced current always opposes the change in magnetic flux. Now let us ask, where does the energy come from? When you push a magnet into a coil, the coil produces an induced current. That current generates a magnetic field which resists the magnet's motion. Because of this opposition, you must apply extra force to push the magnet. The mechanical work you do is not wasted. It gets transformed into electrical energy in the coil. That electrical energy may appear as heat in a resistor, as light in a bulb, or as charge stored in a capacitor. This shows that Lenz's law is nothing but the conservation of energy in action. Energy is not created, it is transformed from mechanical work into electrical energy. Let us solve an example. 3 loops, one triangular, one square, and one circular, move out of a uniform magnetic field. We are asked to find the direction of induced current in each loop. Step 1. As the loops move out, magnetic flux through them decreases. Step 2. Apply Faraday's law. Induced electromotive force equals minus dphi by dt. The minus sign means opposition to the decrease. Step 3. Therefore, each loop produces a current that tries to maintain the lost flux. This means the induced current generates its own magnetic field pointing into the page, opposing the reduction. Final result, The exact current direction depends on the shape, but in every case, the induced current opposes the change in flux. Now let us see another interesting demonstration. Suppose instead of a resistor, we connect a capacitor across the coil. When the magnet moves into the coil, the induced current begins to charge the capacitor. Which plate becomes positive? By applying Lenz's law, we trace the current's path. The direction must oppose the motion of the magnet. From this reasoning, we find that plate X of the capacitor becomes positive when the north pole of the magnet approaches. This shows that Lenz's law not only predicts current direction but also tells us about capacitor polarity in such circuits. So let us summarize everything. 1. The induced current always opposes the change in flux. This is the heart of Lenz's law. 2. The minus sign in Faraday's formula, E equals minus d phi by dt, captures this opposition mathematically. 3. Energy is conserved as external work done is exactly converted into electrical energy. 4. Real-life demonstrations include moving magnets and coils, loops leaving a magnetic field, and capacitors being charged by induction. Lenz's law is not just theory. It explains technologies like electromagnetic braking in trains, induction furnaces in industries, and the working of power generators. I hope this session gave you a clear understanding of how Lenz's law safeguards energy conservation in electromagnetism. See you in the next class with another exciting concept in physics.